Everyone tells you the same story about how everything began. 13.8 billion years ago, there was nothing. No stars, no planets, no light, no darkness, not even empty space. Then suddenly, inexplicably, everything exploded into existence. The Big Bang, the moment when time itself switched on, when the universe burst forth from absolute nothingness into the reality we inhabit today. It's the origin story that science has settled on, the creation myth backed by equations and observations, and the collective confidence of physicists worldwide. Except there's a problem with this story that nobody likes to talk about. The problem is simple but devastating. We have absolutely no idea if it's true. The Big Bang might not have been the beginning at all. In fact, the deeper you look into the physics, the more obvious it becomes that calling it the beginning represents either profound ignorance or comfortable oversimplification. And once you grasp why scientists can't actually know what happened at the universe's supposed starting point, everything changes. Reality becomes far stranger, far more unsettling, and infinitely more fascinating than the tidy narrative you've been sold. Let's start with what we actually know, because the distinction between knowledge and speculation matters enormously here, and most people have never been shown where that line sits. We know with tremendous certainty that the cosmos is expanding. Every galaxy we can observe is racing away from every other galaxy, and the farther away something sits, the faster it's moving. This observation, first documented by Edwin Hubble in 1929, immediately suggests something profound. If everything is moving apart now, then everything must have been closer together in the past. Wind the cosmic clock backward, and you arrive at a state where all matter and energy occupied the same location. A universe that was smaller, hotter, denser than anything we can properly imagine. Calculate how long this expansion has been occurring, and you get roughly 13.8 billion years. That's not speculation or guesswork, that's measurement, derived from multiple independent observations that all converge on the same answer. We can even detect the leftover heat from this early hot phase. The cosmic microwave background radiation fills the entire universe, a faint whisper of electromagnetic energy that represents the cooled remnant of that primordial inferno. Scientists have studied this radiation exhaustively, measuring its temperature, mapping its tiny variations, analyzing its polarization. From this data, we can reconstruct what conditions were like when the universe was just 380,000 years old, the moment when it finally cooled enough for atoms to form and light to travel freely through space. Push further back into the first seconds and even fractions of seconds after this supposed beginning, and we're still on solid ground. Our understanding of nuclear physics lets us predict exactly what should have happened when the universe was 1 second old, how protons and neutrons formed, how they eventually fused into the first atomic nuclei. When we measure the actual abundance of hydrogen, helium, and lithium in the universe today, the ratios match our predictions with stunning precision. The Big Bang framework works spectacularly well for explaining what we observe. But here's where the certainty ends and the guesswork begins. The further back in time you trace, the hotter and denser conditions become. Eventually you reach a point about 10 to the negative 43 seconds after the supposed beginning, where the physics simply breaks down. We call this threshold the Planck epoch, and before that moment, before that inconceivably brief instant, we're completely blind. Not because we lack sufficient data, but because we lack the theoretical framework to even ask coherent questions about what might have been happening. Richard Feynman understood this limitation with crystalline clarity. He would tell you without hesitation that we understand what was happening 1 second after the Big Bang. He might even express confidence about conditions at 10 to the negative 10 seconds. But the actual beginning, time zero, he'd look at you and say, we don't know, we can't know. Not with current physics, and anyone claiming otherwise is selling you certainty they don't possess. The problem is fundamental, rooted in the structure of physics itself. Modern physics rests on two extraordinary successful theoretical pillars. General relativity describes gravity and the large-scale architecture of space-time. How massive objects warp the fabric of reality, how black holes form, why planets orbit stars. Quantum mechanics describes the behavior of particles and forces at microscopic scales, the structure of atoms, the nature of chemical bonds, the principles underlying every piece of modern technology. Both theories work magnificently within their respective domains. The trouble emerges when you need both simultaneously. When you're dealing with something that's simultaneously massive enough to generate enormous gravitational effects and small enough to require quantum description. That's exactly what the early universe represents. All the mass that would eventually form billions of galaxies compressed into a space smaller than an atom. Understanding that scenario demands a theory of quantum gravity, a framework that successfully unifies relativity and quantum mechanics into a single coherent description. We don't have that theory. String theory offers one possible approach. Loop quantum gravity suggests another. Various other candidates exist, but none have been confirmed experimentally. None make testable predictions that we've successfully verified. When you ask what happened at the absolute beginning, you're asking a question that requires quantum gravity to answer, and we simply don't possess that answer yet. Here's where things get particularly interesting, particularly unsettling. When you use general relativity to model the expanding universe and run time backward, the mathematics eventually produces something called a singularity, a point where all matter and energy compress into zero volume and infinite density. For decades, people interpreted this to mean the universe literally began as an infinitely dense point, a mathematical object that somehow exploded into existence. But infinities in physics are almost always warning signs. They're indicators that you've pushed a theory beyond its breaking point, that you're applying equations to situations they weren't designed to handle. When early quantum electrodynamics predicted that electrons should have infinite energy, that didn't mean electrons actually possessed infinite energy. It meant the calculation was wrong, that the theory needed refinement. Feynman helped develop that refinement, creating a renormalized version of quantum electrodynamics where the infinities disappeared. The singularity at the beginning of the Big Bang should be understood the same way. It's not telling us there really was a point of infinite density. It's telling us that general relativity has reached its limit, that we need quantum gravity to describe what actually happened, and quantum gravity might tell us something completely different. Perhaps space and time themselves are quantized, incapable of being compressed below a certain minimum size. Perhaps the universe was extraordinarily dense, but never infinite. Perhaps time doesn't extend infinitely backward at all, or perhaps the Big Bang wasn't a beginning in any meaningful sense. Perhaps the universe existed before in some other configuration, and what we call the Big Bang was merely a transition, a dramatic phase change in an eternally existing cosmos. This opens up genuinely wild possibilities, each one challenging our intuitions about causation and existence. Consider the cyclic universe scenario. Maybe the Big Bang wasn't the first one. Maybe the universe expands, eventually reverses, collapses back into a big crunch, then bounces into a new expansion phase. Over and over, eternally, with no ultimate beginning or end. We used to dismiss this based on the assumption that expansion would continue forever. But the discovery of dark energy, that mysterious force accelerating cosmic expansion, has complicated the picture considerably. Or consider quantum fluctuation as cosmic origin. Quantum mechanics permits particles to spontaneously appear from nothing, borrowing energy from the vacuum, existing briefly, then disappearing. These virtual particles pop into and out of existence constantly at submicroscopic scales. What if the entire universe represents a quantum fluctuation scaled up? What if it literally popped into existence, borrowing energy from the quantum vacuum? This sounds absurd, until you realize the universe's total energy might actually be zero. Positive energy from matter and radiation, perfectly balanced by negative gravitational energy. Quantum mechanics permits zero energy fluctuations without limit. Then there's the eternal universe possibility. Maybe time extends infinitely into the past with no beginning whatsoever. The Big Bang becomes just one event in an infinite timeline, significant but not foundational. This creates philosophical challenges, infinite regress, causation chains with no starting point, but it's logically coherent, and some versions of inflation theory point in exactly this direction. Stephen Hawking offered yet another perspective. Maybe time itself began with the Big Bang, making the question what came before meaningless, like asking what's north of the North Pole. There is no before, because time didn't exist before. But even this elegant formulation doesn't truly resolve the mystery. Why did time begin? Why this particular universe with these specific laws? Why anything at all? Let me tell you about something that deeply troubles physicists. The fine-tuning problem. The universe appears exquisitely calibrated for complexity and life to emerge. If gravity was slightly stronger or weaker, stars couldn't form. If electromagnetic forces had different strengths, atoms wouldn't bond into molecules. If the expansion rate were marginally faster, galaxies would never coalesce. If it were marginally slower, everything would have collapsed immediately after the Big Bang. Dozens of these parameters exist, and every single one sits within the narrow range necessary for a universe like ours. Alter any constant by even a tiny fraction, and you get either sterile emptiness or chaotic formlessness, no galaxies, no stars, no planets, no life, no observers to wonder why. The odds against this happening by chance seem astronomically small. One explanation is the multiverse hypothesis. Perhaps countless universes exist, each with randomly selected physical constants. Most are dead, boring, incapable of generating anything interesting. But a few, purely by statistical chance, get the numbers right. We exist in one of those not because we're special, but because we couldn't exist anywhere else. This is the anthropic principle. We observe a life-permitting universe because only life-permitting universes contain observers to do the observing. Many scientists find this explanation unsatisfying because it doesn't really explain anything. It just relocates the mystery. Why does a multiverse exist? Why do physical laws permit this kind of variation? The deeper question remains untouched. The alternative is that these constants aren't arbitrary at all. Perhaps a deeper, undiscovered theory explains why the values must be what they are, why they represent the only mathematically consistent possibility. We just haven't found that underlying logic yet. Feynman would have disliked both answers. He was skeptical of anthropic reasoning, viewing it as intellectual surrender disguised as explanation. But he also recognized that the universe doesn't always cooperate with our desire for satisfying answers. Sometimes you reach the boundary of knowledge, and the only honest response is, we don't know yet. Now let's talk about inflation, because this concept revolutionized cosmology and fundamentally changed what Big Bang means. During the 1980s, physicists realized the Standard Model had serious problems. Why does the universe look so uniform? The cosmic microwave background has nearly identical temperature everywhere, yet regions on opposite sides of the observable universe could never have been in contact, never could have exchanged energy to reach thermal equilibrium. Why is space so geometrically flat when it could have been curved in countless ways? Why don't we observe magnetic monopoles, exotic particles that grand unified theories predict should be everywhere? Inflation solves these problems elegantly. The proposal is radical. In the first tiny fraction of a second, the universe underwent exponential expansion, doubling in size every 10 to the negative 37 seconds. In an incomprehensibly brief moment, it grew from subatomic scale to larger than a galaxy. This explosive growth smoothed out irregularities, flattened spatial curvature, and diluted exotic particles to undetectable concentrations. Here's the crucial point. Inflation happened before what we typically call the Big Bang. The hot, dense, expanding phase we usually reference, that's actually the end of inflation, the moment when exponential expansion stopped and all that energy converted into matter and radiation, heating the universe to unimaginable temperatures. What we call the Big Bang isn't the beginning, it's what happened after inflation concluded. And inflation itself, we don't know what triggered it, we don't know what ended it. We have models, but they're speculative. Some versions predict eternal inflation, where most of the universe continues inflating forever, with quantum fluctuations occasionally creating pockets where inflation stops. Each pocket becomes a universe like ours. In this framework, our Big Bang was one bubble among infinite others, constantly forming in an eternally inflating multiverse. This is highly speculative. We have good evidence that inflation occurred. It explains too much to be coincidental. But eternal inflation, the multiverse, the ultimate origin, we can't test those ideas with current technology. Here's something most people don't appreciate. We cannot directly observe the Big Bang. The earliest light we can detect is the cosmic microwave background, formed 380,000 years later. Before that moment, the universe was opaque to light. Photons couldn't travel freely because they constantly scattered off electrons in the hot plasma filling space. Those first 380,000 years exist beyond direct observation. We can only infer what happened using theoretical models and indirect evidence. And the first few seconds, those first fractions of a second, we're relying entirely on physics tested in particle accelerators, extrapolated to energies and densities far beyond anything we can reproduce experimentally. We're confident about this physics up to a point, but the Planck epoch represents pure speculation. We don't have the physics, we don't have observations, we're making educated guesses. Feynman would be absolutely clear about this distinction. He'd say, here's what we know with high confidence, here's what we're reasonably sure about, here's where we're wildly speculating, and the absolute beginning falls squarely in the wild speculation category. This doesn't invalidate the Big Bang framework. The universe definitely was hot and dense 13.8 billion years ago. It's definitely been expanding and cooling since then. These facts are established beyond reasonable doubt. But was that the beginning of everything? Was that when time started? We genuinely don't know. If you could ask Richard Feynman what happened at the universe's beginning, here's what he'd likely tell you: I don't know. Nobody knows. We have theories, we have speculation, we have interesting ideas worth exploring. But without a tested, confirmed theory of quantum gravity, we cannot make definitive statements about the Planck epoch. We know about the hot, dense state 13.8 billion years ago. We know about expansion and cooling. We understand cosmic microwave background radiation, nucleosynthesis, structure formation. We have solid theory for all of that. But the absolute beginning, the moment of creation, if such a moment exists, we're guessing. And be suspicious of anyone claiming certainty about time zero. Perhaps the Big Bang was the beginning. Perhaps time started then, and asking about before makes no sense because there was no before. Or perhaps the universe existed previously in some other form. Maybe it was contracting and bounced. Maybe it tunneled from another universe. Maybe it's part of an eternal multiverse where Big Bangs happen constantly, like bubbles forming in boiling water. We don't know. And that's acceptable. That's where human knowledge currently terminates. The appropriate response is acknowledging ignorance, continuing work on better theories, and testing them when possible. Pretending to understand what we don't understand isn't science, it's dogma. But Feynman would also emphasize what's genuinely amazing. We can trace 13.8 billion years of cosmic evolution. We can reconstruct the journey from hot, dense plasma to galaxies, stars, planets, and life. That's extraordinary. That's worth celebrating. The gaps in our knowledge don't diminish our achievements. So if the Big Bang wasn't necessarily the beginning, what's the real mystery? The deepest question isn't when did everything start, but why is there something rather than nothing? Even an eternal universe requires explanation. Even a multiverse spawned by quantum fluctuations raises the question, why do quantum mechanics and physical laws exist at all? Why does the quantum vacuum have properties that permit fluctuations? You can push explanations backward indefinitely. The universe came from a quantum fluctuation. Okay, but why does quantum mechanics work this way? It emerges from a deeper theory. Fine, but why does that theory exist? Eventually you hit bedrock, a point where the only available answer is, this is how reality is, with no further explanation possible. Maybe there's a theory of everything waiting to be discovered, something that explains why physical laws take their specific form, why constants have their particular values, why reality has this structure instead of some other structure or no structure at all. Or maybe at the deepest level things simply are, and explanation terminates there. Maybe why questions eventually stop making sense. This is where physics bleeds into philosophy. And Feynman would tell you, I'm a physicist. I can describe how the universe works. I cannot tell you why a universe exists in the first place. That question might be unanswerable, or it might require conceptual frameworks we haven't developed yet, or it might be fundamentally misconceived. But we can still ask it. We can still push against the boundaries of knowledge and see how far we can reach. So let's return to the beginning, or rather, what we call the beginning. The Big Bang wasn't necessarily the start of everything. It was an event 13.8 billion years ago when the observable universe existed in an extremely hot, dense state and began expanding. What happened before that? Possibly nothing, if time itself began then. Or possibly the universe existed differently, contracting, tunneling, cycling, emerging from some larger structure we can't yet observe? The honest answer is we don't know. The story you learned that everything began 13.8 billion years ago is an oversimplification. It's pedagogically useful but not completely accurate. The complete truth is messier. We know enormous amounts about cosmic history, but the absolute beginning remains mysterious. We're working on it. We have ideas. We don't have confirmed answers yet. Richard Feynman would want you to understand this not to spread confusion, but because he valued honesty, admitting what you don't know, clearly marking where knowledge ends and speculation begins. That's intellectual integrity. The universe is 13.8 billion years old, measured from the Big Bang, but was the Big Bang the beginning? That remains one of science's biggest open questions. Someday we might answer it. We might develop quantum gravity, find evidence of what came before, discover we're part of a multiverse, or realize the question itself is malformed, that time, space, and causation emerge together, making before meaningless. Either way, the search continues. The boundary of knowledge keeps expanding, and that's what makes science beautiful. Not certainty, not having every answer, but the process of asking questions, testing ideas, admitting mistakes, and probing deeper into mystery. That's what Feynman understood and practiced. That's what he'd want you to understand about the Big Bang. It's not the beginning, it's just as far back as we can currently see. What lies beyond? That's the next frontier, waiting for someone to illuminate it.